Hello everyone, I am Chandras Mishra from ABES Engineering College, Ghaziabad. In this lecture, I am going to discuss graph traversal algorithm, which is depth first search (DFS). So here we will discuss graph traversal, depth first search. Then we'll see complexity of this and applications. So let's begin with a graph for which we are going to see traversal. Suppose this is the graph. Like this. This is the graph. Okay. Let's give name to the vertices like 0, 1, 2, 3, 4, and 5. So this is the graph, and we want to do depth first search. So basically, depth first search is based on the concept. First of all, traverse all the descendants of vertex, and then move to the neighbors or siblings, we can say. So here we'll start with the source vertex, that is 0. Let's mark it as the source vertex. We'll start our searching from a 0. So basically here we will use another data structure for the DFS, that is a stack. We already know what is a stack. Stack is the LIFO data structure, LIFO, which means last in, first out. Last in, first out data structure. Basically, what is the meaning of last in, first out? Whenever we access the stack, whatever element is inserted in the last sequence, that will be removed first. That's why it is known as last in, first out data structure. Okay. So whenever we will begin with the algorithm, first of all, we'll create an array, which is visited array. So we'll create visited array here. Let's create visited. Okay. This is visited array. And the size of the visited array will be as it is the number of vertex in the graph. Okay. So here we have 0, 1, 2, 3, 4, 5, 6 vertex in this graph. So we'll create 0, 1, 2, 3, 4, 4, and 5. Okay. So here we will have 0 to 5, that is 6 vertex for this. Okay. And we will initialize this visited array as false in the beginning. The status of all these vertices are false. Okay. And we'll create one stack, empty stack. Suppose this is the empty stack. Empty stack. Okay. So here we are going to start our searching from a 0. So we'll push this 0 vertex onto the stack, and we'll mark the status of this vertex as true. Now this is true. And after that, this what we'll do, we'll find out all the vertices of all the vertices that are directly connected to 0. It means adjacent vertex. So it will be required many times in our program. So let me create an adjacency list. So adjacency list of this graph. Okay. So here we have vertex 0, 1, 2, 3, 4, and 5. So adjacent vertex of 0 is 1 and 2. Adjacent vertex of 1 is 0 and 3. Adjacent vertex of 2 is only 0. Adjacent vertex of 3 is 1 and 4. Adjacent vertex of 4 is 3 and 5. And adjacent vertex of 5 is only 4. Okay. So what we'll do, we'll pop this symbol from the stack and add this symbol to our DFS list. So we'll add this 0 in the DFS and mark it as the visited. Okay. Now what we'll do, we'll put all non-visited nodes adjacent to this 0 in the stack. Okay. So 1 and 2. So let me check the status of 1 and 2. 1 and 2 is false. So what we'll do, we'll just push this 1 and 2 in the graph. 1 and 2 on the stack. Okay. And after this, what we'll do, we'll just mark the status of this 1 and 2 vertex as true in this visited node. Okay. Now come to here, we'll just pop 2 from the vertex, 2 from the stack. We'll remove this and just add to the DFS. And now 2 is visited. Okay, traverse. After this, the status of our stack will be 1. Only 1 is there. And what we'll do, we'll just find out the adjacent vertices of 1. So adjacent vertex of 1 is 0, and so what we'll do, we'll just find out the adjacent vertex of 2 because we have removed 2. So adjacent vertex of 2 is only 0, and the status of this 0 is already true. So we'll not add 0 in this stack. Now again we'll pop the top symbol from the stack, which is 1. So we'll remove this 1 from the stack and add to the DFS list. And after this, we'll find out the adjacent vertex of this 1. So adjacent vertex of 1 is 0 and 3. So we'll push all non-visited vertex of the adjacency list. So 0 is already visited, so we'll not add. 3 is non-visited, so we'll add 3 in the. We'll push 3 in onto the stack and make the status of this 3 as true. Now again we'll pop the top symbol from the stack, which is 3, and we will add this 3 onto the. We have already visited 1. We'll add 3 onto the DFS list and mark it as visited. Okay. Now what we'll do, we'll just find out the adjacent node of 3. So adjacent node of 3 is 1 and 4. So we'll add 1 onto the stack, but 1 is already visited, so we'll not add. And 4 is not visited, so we'll add 4 onto the stack. So here we have 4, and the status of 4 will become true. Now what we'll do, now the top of the stack is only 4, so we'll just pop this 4 from the stack and add to the DFS list and mark it as visited. And now we'll try to find out the adjacent node of the 4. The adjacent node of 4 is 3 and 5, where 3 is already visited. The status of 3 is true. So we'll leave it, and we'll add 5 in stack. Okay. Now again, the top of the stack is 5, so we'll pop this 5 from the stack and add to the DFS list and mark this file as the visited. And now we can see we have the stack is empty and nothing to add into the stack. So we'll stop here, and we'll try to find out, is there any vertex which is not visited. So all vertices are visited, and no need to move further. So now we will stop this, and final DFS list is 0, 1, 2, sorry, 0, 2, 1, 3, 4, and 5. So this is the DFS. So to implement this DFS algorithm, we cannot. It is not mandatory to use stack, because if we are using recursion, or we can call recursive algorithm to implement this, whether polystack is already implemented in the process. So let us see what is the algorithm. How can we write the algorithm for DFS in the pseudocode? So the first step we will do is create an visited an array name as visited. So this is visited array. After that, what we will do, will for each v belongs to the graph, will set the status of each vertex as false. Then for each vertex v belongs to G, we'll call this DFS widget. Now this DFS widget is the main algorithm that will perform traversal for each vertex. Why we need this DFS widget on each vertex? Because sometimes graph may be disconnected. In that case, we need to call this DFS widget for all the vertices of the graph. So let us see what is the DFS widget algorithm. In DFS widget, G is the graph and V is the vertex on which we want to perform uh, traversal, from where we want to perform traversal. So what we'll do, we'll first make this V as the visited, or we can say we'll change the status of visited V as true. Then we'll find out the adjacent vertex of this V. So what we'll do, for all U adjacent to V, how can we find? We have adjacency list of the graph. So easily we can find out the adjacent vertex of V, that is U. We will check whether visited U equals to false. If it is not non-visited, it means what? This is non-visited node. So if the node is non-visited, then only we will call TFS visit on TU. So recursively, it will call all the non-visited node and print that node. So this is the algorithm for non-visited. This is the algorithm for the depth first search, DFS. So what will be the complexity of the this DFS graph is order of V plus E, because whatever will be more, that will be the complexity. If there are very less edges in the graph and vertices are more, in that case it will be order of V. Otherwise, it will depend on the number of edges in the graph. Okay, so this is the time complexity, worst case time complexity of the DFS. Now, if we talk about the space complexity of the graph, so space complexity of DFS, in that case, it will take order of V. That will be the space required to create a visited array. Okay, so these are the differences. Thank you.